Okay, welcome everyone. I know I'm standing between you and the party, so we're gonna go ahead and get started. I'm glad to be here. So I'm going to be going over lessons we learned evolving Uber's Java backend. And so this is not gonna be a greenfield Kotlin story. Uber is not a startup. It's gonna be focusing a lot on how we took a large established Java backend. It's a huge monorepo and how we introduced Kotlin to it. So I'm gonna go through interop, how we got teams excited, the things we're still figuring out, etc. Before we start, a bit about me. I'm on the JVM platform team at Uber. And so you might ask why JVM platform, and that is because my team owns both Kotlin platform, Kotlin language, as well as backend Java frameworks, but we say JVM frameworks here. And so that backend is in Spring Boot. So we're not just writing Kotlin. My team is also responsible for making sure all the other engineers across Uber can do that. And then outside of work, I do a lot of crazy adventurous things, so feel free to ask me about those as well. So here's pretty much what we're going to spend the next few minutes or several minutes talking about. I'm going to start with the why, what the existing tech stack looked like before we started to do this. Then I'll move to how we built the foundation, and then several of the hard and interesting technical problems that we hit to do this methodical introduction. There are going to be code examples in here and technical problems we faced. If you don't want to go that deep, I'm just going to tell you we addressed quite a few gotchas. We had quite a few technical issues, and I'm just going to spend the next 35 to 40 minutes going into all those issues. Cool. So first, let's set the context and why did we think about Kotlin for backend, and what was the existing backend Java tech stack? So Kotlin is not new at Uber. We have an Android monorepo. It's been Kotlin first for about 7 years now. Over 70% of the Android code base is already in Kotlin. All the development's in Kotlin, and we're actively working to migrate the remaining Java. One of the engineers, Idan, did a talk earlier on that work. And in the beginning, there were concerns with using Kotlin. Tooling, impact on build times. Uber uses Bazel as the build system, developer education, and how to actually fund this effort and get that work done. But once those were addressed, the tooling became battle tested across all of our Android projects, Detekt, Rules Kotlin, Coroutines, etc. And so with that, the natural question then became, all this infrastructure exists, can we just bring it to the back end? The short answer to that was no, not as much as we thought, and in fact, we had to rebuild a lot of it, but that's what this is about. Now, think about developer satisfaction. Once Kotlin was introduced on Android, I will point out these figures are from around 2019, 2020. We are an AI-forward engineering company. These numbers will be different, especially on backend, because of AI coding. But the big ones to call out here are the increase in changes per month, reduction in code complexity, and the increase in developer satisfaction. And this translates to what we really cared about measuring on the backend, right? Can we reduce boilerplate? What about async programming paradigms with using Kotlin coroutines? Can we reduce nesting, call depth, etc.? And just if we have production issues, how easy is it for developers to diagnose this? So Uber's mobile Kotlin landscape was the baseline. And so the ecosystem we already have at Uber, built over many years on mobile, 6 Android applications. This includes the Rider app, the Uber Eats app, so you can order all your delicious food, and the Driver app that drivers use to figure out who they need to go pick up and drop off. Again, 74% of the source code is already Kotlin, and we have about 14,000 Bazel modules. And so again, it's production-tested infrastructure that has been used for many years. Now, if we look at Uber's backend Java landscape to contextualize this, a lot bigger than the mobile set. Uber runs on a massive Java ecosystem, and everything's interconnected. And we do operate out of a single monorepo using Bazel, which does give us consistency, but it does mean that every change we make pretty much affects everyone immediately. We are currently running on Java 21 across the board. There's an active migration to Java 2025, Java 25. And so this is a constantly evolving ecosystem with changes happening all the time. So when we did this, every decision about introducing Kotlin became an architecture decision that we had to look at from an architectural standpoint, not just a let's introduce a programming language. And that context did shape every decision we made. And I do want to call out here, the goal was never to replace Java on Java backend or rewrite everything on backend into Kotlin. This was just let's add the option and be methodical and give engineers that support, especially starting with the strong use cases that Kotlin can structurally solve better than Java can. And so 4 problems actually drove us towards supporting Kotlin, and these are all from real production issues and code reviews. These aren't just theoretical. So the first one was heavy resource usage. As we know, traditional thread per request models under high concurrency can consume significant memory. The second one was complex async paradigms. So things like completable feature chains, callbacks, deeply nested code. And so, each async step can add nesting layer, and each error path splits, and it just increases the code complexity. The third one, race conditions. Java's starting model makes it easy to accidentally share mutable state. Kotlin doesn't completely eliminate that, but it makes it harder structurally. And then the final one, unsafe null handling and MPEs. Java has no compile time null enforcement. Kotlin does at the type system level. And so, yes, platform types can get you if not handled correctly, but Kotlin does have this at the type system level. And we didn't really go into this blind. We looked at what large companies have already done. So the Kotlin website has case studies from several other large companies that were adopting this for backend. And so this industry signal was clear, and this wasn't a problem that was specifically unique to Uber. And before we actually started to build this out and write any code, we ran an internal study for backend. And so the big ones to call out here is the process and tooling priorities. The ones I want to call out are the confidence that Kotlin can safely coexist with existing Java modules. Again, this was an established ecosystem. We don't necessarily build a lot of greenfield services daily. Code quality and linting, and then clear guidelines on when and where Kotlin is appropriate versus using Java. And the 43% interop confidence is the big one, because developers weren't asking for Kotlin features first. They wanted to know, if you put this in here, are you going to break what already exists and is running in production? In terms of features, coroutines, not surprising. And then null safety and type inference, again, services are suffering from null pointer exceptions. Data classes for concise modeling, and then extension functions and DSLs for some of the work that we do also came up. And so we shaped our prioritization off of this. And again, we didn't treat this as a hard launch, but as a gradual rollout to see what that would look like. And then we got explicit leadership approval, and we tried to figure out what would success look like for all of this. Okay, so now we know what developers want, and so we began this infrastructure work in the second half of 2025. And so we started with the toolchain, static analysis, and thinking about production safety. And so I mentioned before, we have a large Android monorepo with a lot of that tooling. And so this assumption that we had going in was Android has all of this production tested tooling, and we can just reuse it. And in actuality, we could not reuse it directly. And the reason is that Android tooling was built for Android, and it has hard dependencies on Android-specific concepts that really don't exist in a backend environment. And so every tool and corresponding configuration we tried to import had some dependency that blocked it. And so that head start that we thought we were going to get, we kind of had to rebuild a lot of stuff from scratch. And specifically, these are the tools that we had to work with. So before a single service, Kotlin service could land in production, we had to rework a lot of this tooling. So everything from build rules with Bazel, CI integration, Detekt, formatting, code coverage, because we didn't want to introduce any tooling gaps to an existing ecosystem, so that way developers hit this point where, oh, well, if I use Java, I have static analysis. If I use Kotlin, it's the wild, wild west. And critically, one thing that we want to do is introduce all that tooling at the latest release version. The problem with that is that the Android monorepo was not necessarily at the latest version of libraries or language, and so we actually introduced version drift accidentally, and then because Kotlin has an upgrade cadence about every 6 months, or whenever a new library is released, you get more version drift. So going down the list, we're going to start with the Bazel rules. Uber Android uses an internal fork of rules Kotlin for Bazel. That internal fork was branched from mid-2024. And the problem is that because it hadn't been rebased recently, our backend repo actually couldn't use it. And then we started to wonder why. And after we did some investigation, it turns out that in rules Kotlin before version 2, the Kotlin compilation worker for both JVM and Android were bundled together, and it baked in the Android dependencies. And because this was a backend monorepo using Bazel, we didn't want to have to be responsible for configuring all the Android toolchain as well as the Android configurations for a backend environment, especially when it's not needed, because now that just becomes a maintenance burden. So in open source rules Kotlin v2, this functionality was split, so you get jvm.bazel and android.bazel, which become fully independent entry points, and then the JVM path no longer requires Android. So backend uses upstream rules Kotlin or open source, and Android does not. But the problem with that was that once we started to use the open source for backend, it meant that every internal optimization that Uber had built was unavailable for backend. And the big ones were code coverage. Android uses cover, and so backend has to use Jacoco because cover requires the Uber fork, which also requires Android. Internal build optimization, so we had work around faster incremental compilation, custom remote execution tooling, and Uber-specific Bazel extensions, and none of those transferred directly. And because of this, this became an ongoing cost and not a one-time gap, and the maintenance delta just kept growing. So in backend, we just have a clean Bazel dep, as you can see from the screenshot here. We just depend on jvm.bazel, and then we can just load all the JVM build rules, and we don't really have to configure anything for Android, no toolchain, no provider, etc. Next up was code coverage. So cover is the idiomatic Kotlin coverage tool. Yes, you can use Jacoco, but cover is the idiomatic one. And it's what Android uses. And for consistency, which was a big bit of this too, it's what we wanted to use for backend. But the problem was that cover and Bazel required Uber's fork of rules Kotlin, which required the Android Bazel provider, which again isn't needed in a backend environment. So to solve this in the short term, we shipped it with Jacoco as a short-term solution, and it works, but it's really meant for Java, not necessarily for Kotlin. So rather than staying blocked, we actually are working on upstreaming our internal change into rules Kotlin upstream. And so that way the broader Bazel ecosystem can just benefit from this. So that way any team running Kotlin backend with Bazel can use cover support if they want to configure that as well. Next one up, especially for backend, was the IDE gap. So yes, the keynote mentioned LSP improvements. It's gone to alpha, and so that will help us in the longer term. And again, Android developers use Android Studio. So the Kotlin support is just built in natively. You just load Android Studio, you get type completions, auto completions, etc. Backend developers at Uber can use both IntelliJ and they can use VS Code, and we have a sizable population that use VS Code as their day-to-day programming IDE. And using VS Code without that LSP, you essentially just have a very nice text editor. And so this is one of the areas that's still open, and we're really not yet at the Android parity here. For those developers that want to use VS Code, we pretty much have to tell them, hey, if you want to use Kotlin, you have to go to IntelliJ. Now, we did find a somewhat hacky workaround around this, and so we just load the official Kotlin LSP as a VS Code plugin. It's now officially on the store, but we were just downloading it from GitHub and then just loading that into the IDE, and it wasn't perfect, but it at least solved some of the critical use cases. Next up on the list, which is pretty important at Uber scale, was testing. So we had a test runner, but there had never been a single Kotlin target in backend before, and the JUnit 5 runner had actually never been registered for Kotlin targets. And so tests would compile, and they'd pass review and get committed, but they wouldn't actually run in CI. And there was no error and no output. It was just silence. And this is one of those gaps that you really only surface when you're the first person to do something, and then you wonder why, hey, I changed this, and this test should fail. Why is everything passing? And this fix wasn't a test runner replacement. It was just we added a JVM flag inside our Kotlin Bazel macros. So when we set up the test arguments in Bazel, we just append for Kotlin targets this JUnit 5 equals true, and that gets added for every Uber KT target automatically. And the important part here is that Java targets don't get this, so we're only changing the Kotlin build path. And then the Java path can still use JUnit 4, and then we get zero risk of breaking those tests, and then it also let us introduce JUnit 5 for Kotlin without touching all the Java test infrastructure. Then we just updated our test runner, and so if the Boolean is set, use JUnit 5, otherwise keep the existing path for JUnit 4 in the test runner. Last up on that list was static analysis. So Java uses error-prone, which is a compiler plugin. Kotlin uses Detekt automatically, which is a standalone tool, and they have completely different APIs, right? You get bug checker versus role, visitor state versus binding context, suggested fix versus code smell. Error-prone can automatically fix things, because Detekt can tell you, hey, this thing shouldn't be like this, but it can't just automatically do it for you. And so nothing really transfers directly, and every existing enforcement that we had, whether it was custom or error-prone was giving it, had to get ported over in some way. And so we had to break this down and audit these into 3 categories. We had net new rules that we just wrote to say, hey, this is important for our backend, and custom rules we had. We had copies from our custom Android Detekt rules that we then had to adapt for backend. And then we had full ports from error-prone where we said, hey, this thing exists in error-prone. It's really cool, and it also applies to Kotlin. Let's add a rule for this. So the big point here is that even when the rule concept is identical, you might have to change stuff from a mobile environment to a backend environment, and we spent quite a bit of time doing this as well. And one example of this we had was public top level. So in our Android version, it's just as simple. You visit the name function detect. There's no exclusions, and you say it's a defect because in Android, you don't really need to have public top level, keep the namespace clean, all those beautiful things. And so you can just see the logic is clean. It's just if it's a top level and it's public, then report it and say, please don't do this. You need to go change something. But that story is not as straightforward on a backend. So it's the same rule and the same intent, but we did have to adjust the configuration for Spring Boot services. And so the biggest bit to note here is that in the middle, you can see we added this configuration annotation, and we said exclude these function names from this check. And the reason we have to do this is because on a Spring Boot service, you do need a public top-level main function. And so we also have to change the severity from defect to maintainability because it's no longer a defect, because you do need to have a public top-level main, but maintainability-wise, we don't want to have a polluted global namespace. And so the rule logic is identical, but we did have to do some updates into the logic itself. And then in the configuration file for backend, what we then did was we added exclusive function names, main. Again, every Spring Boot service needs this. And then this did introduce some configuration differences between backend and Android. And so again, Android will configure things like Jetpack Compose rules. Backend does not need that. Again, you also have rules on backend that will take extra configurations or different configurations than mobile. And the problem with this, though, is that the config drift between the two becomes the default, and now we have to actively synchronize them to make sure that if we change stuff in one, we change stuff in other to give that consistent developer experience. So now we did that, but now we have to wire everything together into Bazel. And interestingly, in our internal setup, we noticed that on the Android side, there was this isAndroid attribute in the rules. And it actually wasn't quite clear what it was doing. So we investigated, and we actually found out that this isAndroid attribute was actually enabling type resolution for Detekt. And what it was actually doing was it was determining whether we included the Android or Java jar getting added to the class path to do the type resolution. Additionally, we also discovered that it made a change such that we never could run in light mode, which is valuable in some cases, and we were always enabling it in full mode for type resolution. And so again, another good example where the Android-specific assumption kind of baked itself in accidentally, and it's not that it was never intended to block a backend environment. It just was made without thinking about backend at all. So we fixed it. We made it more resilient, and then we worked to upstream this. And so you can see here, instead of just saying isAndroid, we just say enable type resolution. This is actually, if you go to that URL, this is an open PR right now. And we set it to false, and then if it's true, we do a bunch of logic under the hood to say, okay, if this is true, figure out, do you need the Java jar or do you need the Android jar? And then it bundles that in. And this is a good example where open source community engagement is good in practice. We reached out to the Detekt maintainers and asked them, hey, would you be okay if we did this? They said yes, we upstreamed it. And this is also a good lesson of every fix you upstream is also just one less thing you have to maintain internally, and it also just helps the whole community. Then, because we have Detekt v2 coming, we then decided, all right, let's also add support for Detekt v2. Uber is trying to go to Detekt v2, and so we upstream this as well. Because in Detekt v2, they just change it. So now there's an analysis mode flag, so we said, all right, now just simply change the attribute, make sure the docs are up to date, and then we simply just change the condition in the impl to just say, instead of it being a Boolean, enable type resolution, just see if the analysis mode is full and everything else got to stay the same. And again, the community benefits, we benefit, and it's now open source, so we don't necessarily have to maintain it ourselves. We also upstreamed a bunch of other changes as well. If you go look at the open source, we have quite a few bits here, and once these are merged, pretty much anyone who uses Bazel rules Detekt, you will get type resolution as well. All right, so now we fixed the Detekt rules, and then finally, to make sure that developers could not accidentally forget to run static analysis, we updated the Uber Kotlin library build rules so that way it automatically creates a Detekt target for safety. So once those targets get built, you just get a Detekt target that is registered with CI automatically, and so static analysis will run, and developers don't really have to think about this. Cool. All right, so we've done all that, and so now we have all this infrastructure and tooling finally set up. Now we look at the why did we actually want to do this, right? And so this is, coroutines were the big technical selling point in the beginning to get funding for this effort. And so now let's look at what the coroutines value did. And again, we're looking at why coroutines. So as I mentioned before, many existing Uber services face challenges with race conditions, asynchronous programming complexity, and they often are actually consuming heavy compute resources. Manual cancellation is easy to forget, so we are getting memory leaks. Race conditions emerge from shared mutable state across the threads, as Java's model requires you to opt into safety with synchronized blocks, locks, volatile keywords, etc. But coroutines flip this on its head, as we all know. The structured concurrency enforces that parent-child relationship automatically. Cancellation propagates down. Code looks mostly sequential, easier to read and work through. And then race conditions are just structurally harder to introduce in the code itself. And so here's an example as a completable future chain. Typical Java async code in backend today. Multiple sequential async calls chained together. You get the then compose and exceptionally, and you really have to think through this and hold this in your head to really understand what this logic is doing. And then there's split control flows and just extra lambdas in here as well. So that makes debugging, stack traces, and just raising about the state all harder because those lambdas get introduced. And to be clear, this works. I mean, this is production code I pulled. And it does have a cognitive cost, though, and this does compound as this gets more and more complex. But if you use coroutines, what changes? You see we no longer have those then compose chains. The exceptionally is gone. You just use the standard try catch. And then suspend is really just the only signal that this function is even async, right? And then, again, the compiler now enforces that you can only call this from a coroutine or another suspend function, so you also get that as part of the type safety we were talking about. The other big bit here, though, is I needed actual data, though. So intuitively, we say, all right, coroutines are great. They're going to be better than standard threads, et cetera. But I needed data and not intuition. So what I did was we ran our own internal benchmark through simulating work. I wanted to gauge our hypothesis before we committed to coroutines and actually really sold it, right? And so then I also asked JetBrains to spot check some of that logic. So shout out to JetBrains for helping us with that. And essentially, we observed that Kotlin coroutines are the most scalable and memory-efficient choice for high concurrency workloads on the JVM. Again, these, we were just simulating work of like delays and such. I'd also like to point out that these graphs are in logarithmic scale, and the reason is that if you don't, coroutines are just this flat line at the bottom and everything else just shoots up, so you don't even really see coroutines on the graph. But the entire point of this was that we were almost empirically able to prove that coroutines were the way to go long term. So now we've got coroutines going. But then we looked into our services, and we ran into this very interesting backend problem, which is a bit unique to Uber, and that's request context propagation. And so you might ask, what does request context propagation mean? And so we use Uber context, and it's a standardized request context framework that we use, and it carries tracing, auth tokens, request metadata, et cetera. So that way, as a request goes through different services, we can see where it originated and the entire lifetime of that path for tracing and observability. And the thing to note about this is that we actually store this in thread local storage, which is tied to the thread. So Java, this is safe, and the same thread will handle the entire request, and thread locals are always present. The problem that we have now run into is that Kotlin coroutines can suspend on thread A, and then resume on thread B because it's switched. And so thread locals no longer follow. So when we try to resume the coroutine and get the Uber context, we actually get nothing, and there's no exception, and you just get a null object. So now we've lost the ability to trace this through. So again, Java's fine. Threads don't switch during execution. Kotlin, they can. So we took the naive fix originally, which was use thread local.as context element. The problem with that is that it requires every caller to explicitly wrap their context. And in a large monorepo, statistically, someone is eventually going to forget, and nothing at compile time will catch this. So now we've introduced a critical risk by actually trying to make something better, right? The request context propagation depends entirely on developer discipline across thousands of engineers writing many diffs, and it's just a recipe for silent production failures. And so we realized this isn't really that scalable. So to get a scalable solution, we needed to find one that works for every coroutine, everywhere without manual developer action at the code level. And so we had this insight, and that it's every Kotlin suspend function will compile to a state machine, and that state machine extends base continuation impl. And there's always exactly one method that will run every time a coroutine resumes, and that is resume with. So we looked into ByteBuddy, which is just a code generation library for creating Java classes, and we realized that if we instrument base continuation impl with ByteBuddy at the JVM startup, we can propagate Uber context automatically across every suspension point with no wrapper functions, no as context element, and no manual code opt-in required for developers. And so there's three hooks that we had, which is the constructor, which will capture the context on the launching thread. The resume with entry will then install it on the resuming thread, and resume with, when it exits, will just recapture any modifications and put them back. And so what this looks like is this is the ByteBuddy agent setup. Again, you can see here we target Kotlin coroutines, JVM, internal base continuation impl, and we just ignore everything else, and so we only need to instrument the one class. And then we have a retransformation strategy, and that just means it works even if base continuation impl is already loaded when the agent starts. And then we install two pieces of advice, the constructor advice, again, for the constructor bit, and then resume with advice on the resume with method. And so the agent thing is installed via the JVM's pre-main hook before any of the application code actually runs. Then when a coroutine is, or when a continuation is constructed, on the launching thread, we capture the current context storage, and we store it in a weak hash map, and we key it by the continuation instance. And weak hash map here is intentional, so that way when the continuation is garbage collected, the entry is automatically cleaned up, and you don't get the memory leak. And so this will run on at on method exit after the constructor completes. That way, self and this is fully initialized. We also add suppress equals throwable. So if anything goes wrong here, we just swallow it and move on. We don't want to crash the production application because of this, as the request context propagation is mostly best effort, but we want to get it where we can. And then here on enter, it will run when the coroutine resumes. and it will just do it on whatever thread the dispatcher chose. So then we just go into we look up the stored context storage, and then we install it on the current thread. And then the snapshot returned by set context will capture the thread's previous states. That way we can restore that on the new thread. And then on exit will run when the coroutine suspends or completes, and then we recapture that context and then restore the thread's previous states. That way we keep things and make it seem like they're all operating on one thread, even though it can jump. And so this is just the enter, install, and exit restore patterns. That way we can come in, make some changes, and then pull it back out. And then the thread's context is left exactly as it was before the coroutine ran, so that way another coroutine can run on that thread as well without getting any tracing issues. And then in the service config, you just have to add these 2 lines. Everything else was the actual internal implementation. And so in the Pinocchio config, you just set these 2 properties. And so any service can opt in at the service level. And there's no direct code changes required from developers. They just get all of this for free. And so this was really the point of using ByteBuddy, is that developers can't forget to do this so we don't lose all of our context, request context propagation. Cool. So that was a lot, and we learned a lot throughout this process. It was many months of work. And so there's 12 lessons I'm going to go through, and the real ones, they're going to be things that are good, things that I would probably redo going back through this. And these came mostly from just hitting walls, rebuilding assumptions, and just experiencing these issues in the day-to-day. Number 1, your Java ecosystem's health is your Kotlin adoption starting line. So in the beginning for backend, our bottleneck wasn't actually Kotlin, it was actually the existing Java ecosystem. We had an old version of Spring, dependency complex, and libraries nobody had modernized and upgraded for years. And so all that became a blocker as we tried to add the Kotlin support. And so what you already have will determine how fast you can move going forward. And so while we thought the toolchain would be the hardest part, it was tricky, but it actually wasn't. The state of the Java ecosystem underneath it was. Number 2, focus on the toolchain first, but make sure you validate with real code. So oftentimes the temptation becomes land the Kotlin code and just figure out the toolchain as you go, right? We just want to write the Kotlin code, get it into the code base. I would say don't. As we saw with the test runner example, if that fails, it fails silently. CI can catch what the IDE misses, and developers lose trust fast. And trust is hard-won and easily lost. So the JUnit 5 runner not being registered was a great example. The test compiled, they passed review, they got committed, you think they're running, but they just weren't, and nothing told you they weren't until you had to intuitively think, oh, I changed this, why did that test not fail? 3, incrementally better is not enough for feature teams with higher priority work. And I think this was probably the hardest lesson I learned organizationally while doing this. Kotlin is better at doing this thing is not enough to get a production team to take on risk and disruption, especially when they have a lot of feature requests coming in. Every team has a backlog. Kotlin, and honestly just most platform and infrastructure work, they don't often appear in that backlog unless they're solving something super critical and urgent, or you have a senior VP or a CTO who's just saying you just have to do this, right? And you also find this in a lot of other areas too, right? Teams working on new services or already doing migrations will somewhat adopt a new thing if there's very little friction. When there is not very little friction, it becomes a harder push. And so especially teams working on new services and teams asked to adopt it for its own sake do not. And the urgency has to already exist. You can't manufacture that urgency. Your job, especially on a platform team, is to go find it and make sure that, hey, we can structurally solve this well for you if you do this. Number 4, Android tooling does not port to backend for free. Again, we assumed that we'd get a head start from years of Android Kotlin tooling. I truly thought we could copy and paste and be done in like a week. But again, almost everything had a hard dependency on the Android ecosystem itself, the Bazel provider, et cetera. And again, those really don't exist in a JVM backend environment, and they really shouldn't. Again, things from Detekt rules, code coverage, build rules, almost everything has to be rebuilt from scratch with inspiration from the existing Android code. So the lesson here is assume zero transfer until it's proven otherwise. Even rules that looked portable on the Android side often did Android-specific things, and we realized, oh, wait, we can't just copy this in, as we saw with public top level. Yes. All right, 5. 2 monorepos means 2 of everything. Automate it or accumulate debt. And when I say 2 of everything, it's probably 2.5 of everything, because we're always in a migration state. So every decision you make in one repo is now a decision you have to consciously mirror in the other, right? So the Detekt example is one of those. Make sure you keep those configurations in line, otherwise you get an inconsistent experience. All will drift silently if you don't actively do that synchronization. We had config drift pretty much immediately because Android had some defaults that just didn't even make sense on backend from the get-go. Rules that were added to Android actually weren't reflected in Backend. There were some rules that were added and weren't even turned on. And then we turned them on for Backend, and there was that drift as well. The fix here, though, is automation, not necessarily developer discipline. Discipline doesn't scale across 2 huge monorepos, multiple engineering orgs, and then a Kotlin release every 6 months, right? Things are inevitably going to drift if you don't find some way to do this sublinearly. And again, if you're running Kotlin in multiple repos, build this synchronization tooling early. Don't wait till the drift has accumulated, because now you have to synchronize it and reconcile it. And so for Kotlin, we've been investigating using Google's copy-bearer tooling, which lets you copy source code back and forth. So we're looking into how we could use that to essentially mostly solve this problem for us. 6, version drift between monorepos multiplies every upgrade. It's something that I've been working through the past few months at Uber. And so again, Kotlin ships a new version about every 6 months. And every release, the minor ones can include breaking changes. Libraries will also upgrade periodically as well, some more than others. And so when Android and the backend drift to different Kotlin versions, a single upgrade becomes 2 separate migration efforts with 2 separate breakage services, and they will break in different ways. And so you essentially have double the amount of work, because again, you can't necessarily just copy and paste. We've run into things with Bazel cache invalidations. Toolchain behavior has been different due to underlying configurations and libraries, and different interop edge cases, and these have all compounded over time. So version parity is a maintenance contract. Don't think of it as just something you can just set later. You want to set that in the beginning. Number 7, greenfield is easy. Existing services are where the interop discipline really matters. So teams building new services were enthusiastic. They got a clean slate, no existing Java to interact with. Let's just use Kotlin and move forward into the light. The teams adding Kotlin to existing Java services were nervous, and rightfully so. Null handling, platform types, mixed sources and build targets. Is this going to affect build times for developers? Differences in the annotation processors, and they all surface in existing services, not the greenfield ones. So you can't use greenfield adoption as a strong signal that interop is working, because it isn't until you've tested the mixed Java and Kotlin source that you really start to see where are these rough edges. And so the services we intentionally began with when we did this, they were lower criticality services, which meant less traffic, but a smaller blast radius if something goes wrong, because it's not as critical in a production environment. The early adopter model of those services wasn't just about blast radius. We really wanted to get the interop signal before we started to go into more of our critical services. 8, interop exists, but it has rough edges, and ultimately those edges are our responsibility. Again, platform types, Java can hand you a null, but Kotlin will treat it as non-null, so you get a silent MPE at runtime, and you don't know it until you've hit that code path. Completable feature to coroutines, not automatic as much as I would love it to be. There is bridging code that's required, or you essentially end up accidentally blocking the coroutine dispatcher, and you lose the benefits of coroutines anyway. JVM static and JVM field, explicitly designed. You have to think about it at every Java-facing boundary, because it's really not optional for Java callers. They'll get these quirky APIs that actually end up not being Java idiomatic. And again, we want to work for both Kotlin and Java idiomatically. And again, these aren't really bugs. They're just, you have to own them. You have to think about them. And they really exist because ultimately you do have 2 different programming languages and 2 type systems that are meeting at a boundary. And so the answer is intentional design, not just hoping that things are going to work, because the famous saying, hope is not a strategy. Number 9, and this is a very big one. Find the team who's paying Kotlin solves and then make them famous. What I mean by this is adoption doesn't magically manifest itself out of the sky. Teams are busy, and again, Kotlin is great for X, Y, and Z isn't a reason for teams to want to take on risk. So the question you need to ask is not who wants to try Kotlin, it's who has a very serious problem that Kotlin can structurally solve and solve really well. Again, async heavy code with race conditions, a team that might already be mid-migration for some stuff, where if they're already migrating, they might say, hey, it's easier for me to migrate to coroutines versus React 1 to React 2, for example. A greenfield service with no existing Java, also a great contender. And the big bit that you have to remember is that organizational cost of adoption is real, and the mixed language expertise on a team, again, we have to maintain 2 Toolchains, and there's a code review burden when people have to mentally switch. And so that cost has to be offset by the pain point that they're already feeling. And then when they do succeed, make sure they tell that story loudly with data and make them become the advocates. A team with real data that is advocating for Kotlin is going to do way more than I can ever do just walking around Uber saying, use Kotlin, use Kotlin, use Kotlin, right? And so adoption becomes this pull motion, and you have to make that success visible and make them want to come to you versus you having to go to them and beg and say, please use Kotlin. Number 10, leadership wants measurable business value, not just enthusiasm. I mean, enthusiasm's great, it's engineering. But every leader that I ended up talking to, whether that was a director or VP, we always got the same thing. What is the cost of having you add the support? What is the ongoing cost? And then what is the actual benefit we're going to get for services? And again, Kotlin is safer. We're going to get less MPEs. Great. But that's not the answer that leads are looking for. It's mostly a pitch for other engineering teams to go use the language, right? Measurable business value, this is going to be things like reduction in incidents, resource footprints. Again, we would like to use less memory and less runtime. Production safety, development velocity are all the things that they care about. So if we can say, hey, if we use Kotlin and we reduce incidents by X percentage, that's the part that they care about, right? And again, adding another development language has real ongoing costs because now we have to think about tooling. We have to upgrade the language. They just announced Kotlin 2.4 today, which means we now need to go migrate to that. There's developer training, and then we have to keep those versions in sync. So make sure you define those metrics before you start and not after, because if you do wait until you need to justify it, you won't have the data to justify it. Number 11, engage with the open source community, contribute upstream, and collaborate. So as you saw, we hit quite a few limitations and issues in Rails Kotlin, gaps with Detekt, and then edge cases in Detekt itself. Rather than working around them internally and creating forks, which I would just have to maintain forever, and I'd really rather not do that, we went upstream. And actively engaged directly with the Detekt maintainers. JetBrains has been super helpful. We filed UTrack tickets, and they've helped us work through those, as well as other maintainers of other libraries. And every fix you upstream is just one less thing you have to maintain. And again, the community will also have context and perspective you don't. I am not a Detekt expert, but the Detekt maintainers are. And if we're running into an issue, we can just say, hey, here's an issue we've run into, and they can help us fix it, and we can contribute engineering effort back to that as well. And again, we're also at KotlinConf, so this is arguably the perfect time to go network with those people anyway. Cool. And then number 12, the work doesn't end at the first service, it evolves. And I'm not standing here telling you we have it all figured out. In fact, I'm still actively in the middle of this and trying to figure out a lot of this stuff. So open challenges, we're still facing LSP gaps. We're still trying to make sure that Bazel build time doesn't increase on Kotlin. We're still trying to migrate to Detekt v2. Again, Seva and team have announced Kotlin 2.4, so that's now going to be a thing I need to think about next week. And if you go into a Kotlin backend migration expecting a one-time project with a clear finish line, you're going to be surprised and a bit disappointed because it is infrastructure, and it does need owners, a roadmap, and a maintenance budget with teams staffing this. And again, now that you think about it, the context is shifting underneath us, right? It's Uber's doing AI-forward engineering. And in an agentic world, right, agents can generate boilerplate, handle those repetitive Java patterns, and reduce the cognitive cost of verbose code. And so you have to think, do Kotlin selling points still hold in that world? Do they become less relevant? Are there new metrics that we need to figure out to go, hey, what is the next thing that we need to work on? Cool. All right, I've covered a lot, learned a lot, and the things I want you to think about are, this is an adoption story, right? And it's not just about Kotlin, though. It's about this gap between this is better versus this is what's worth disrupting team priorities for, to say, hey, you should really use this because it solves a problem. And that gap is real, and it's there because I live through it every day. But in an agentic world, again, AI everything, that gap is changing, right? So again, agents can write the boilerplate Java as fast as Kotlin removes it. So where does that go, right? Does that productivity argument shrink, right? But things to think about, coroutines and compute efficiency, you can't agent your way into structured concurrency, right? You can try to prompt Claude as much as you want, but at the end of the day, that's an architectural thing that does still become a benefit, right? Things like safety, so null safety, type safety, et cetera, they actually matter more, in my opinion, when agents are generating the code, right? Agents make mistakes, and they hallucinate every day, right? But the type system will catch them at compile time. So if it makes this assumption, oh, this thing is not null when or this thing is nullable when it should be not null, the compiler can now catch that, right? And so the things that I've noticed recently, too, is that the teams are asking, should we invest in this language? What should we be thinking about? They're also asking, what does it mean for us to adopt Kotlin if AI can eliminate some of the issues that we experience with Java, right? And so that's my parting words to you. So thank you, and please vote.